Okay, so good afternoon. I am Thomas Boniou, a first-year PhD student from the Laboratory of Solid Mechanics at École Polytechnique under the supervision of Véronique Doquet, and from the French railway company SNCF under the supervision of CIMI. And today I will talk about crack propagation in railway steel. So rails are submitted to rolling contact fatigue, which can induce several types of crack. For example, the squat type here, which initiates due to the very high cumulative shear plastic strength at the top of the crack, and then keeps propagating in a highly shear plane for depths much larger than the initial classified layer. And the time evolution of the stress intensity factors at 2 points along the front of a 6 mm deep crack inclined by 75 degrees towards the horizontal axis were computed here. And those are plotted versus the load position, which is equivalent to the time scale. And okay, so the 2 points are here the deepest point on the crack front and an intermediate point on the crack front. And we can see here that when the load is far away from the crack, the rail will bend upwards, thereby inducing some mode 1, some opening. And as the load gets closer to the crack, the rail will bend downwards and the crack will be closed but sheared. So we have a different proportion of mode 2 and mode 3 depending on the position along the crack front. And if we plot the loading path here at the deepest point in the K2, K1 space, and in the K3, K1 space for the intermediate point, we see that the loading is non-proportional and nearly sequential, with the predominance of the shear mode over the opening mode. And usual criteria will predict bifurcation of the crack, which with such loadings. But in fact, the crack keeps propagating in the same plane, and so existing models are not satisfactory for this type of loading, and we can wonder how to predict the crack path and crack growth rate in this case. So this thesis is focused only on crack propagation and for quite long cracks. And our experimental approach will be based on mode 1 experiment, some mixed mode 2 and 3 experiments, and some non-proportional mixed mode 1+2 and 1+2 and 3. But at the time, only the mixed mode 2 and 3 experiments and some mixed mode, non-proportional mixed mode 1+2 are done. And today we are going to discuss the mixed mode 2 and 3. So many studies focus on mode 2 and mode 3 alone, and the results tend to confirm that the effect of friction and roughness have to be taken into account. But only a few studies focus on combined mode 2 and 3. We can cite, for example, Kelly and al., who did some unsymmetrical 4-point bending on bars in order to get the thresholds while ignoring the friction. Kokla, Vostok and al. did some studies on a sheared cylinder with a circumferential notch, and their studies were focused on the mechanisms, while friction was prevented by a compressive pre-cracking. Doke and al. did some studies on the same device as Elier, mostly focused on kinetics, where friction was taken into account. And recently, Flavien Frémine and Sylvie Pommier did some studies on a cruciform specimen, focused on kinetics, where friction was prevented by using the static K1. And within this limited number of studies, we don't find any friction-corrected kinetic data for mode 2 and mode 3 in rail steels, so we have to perform the experiments. Okay, so in our case, we choose that we used the device developed by Elier, which is a bar loaded in unsymmetrical 4-point bending, and this bar has a notch and a pre-crack in the middle of its length. And if we take a look at the forces inside the specimen, we can see that there is no bending moment in the middle, which means no mode 1. But we have some shear forces, which will induce some shear modes, and the sample can be rotated around its axis by an angle alpha. And by doing so, we change the orientation of the pre-crack front towards the applied force, which will change the mode mixity. but the counter effect is that it will be hard to get direct imaging of the crack, since the sample will be rotated in the testing machine. So I performed some finite element simulations in order to get the stress intensity factors profiles along the crack front. Yeah. So for alpha equals 0, mod 2 dominates. This means the horizontal crack front. And for alpha equals 90 degrees, which means the vertical crack front, mod 3 dominates. But in each case, the other mode is still present, especially on the sides. And we are always in mixed mode, except in the middle of the specimen. So each experiment will provide us with several kinetic data depending on the position in the crack front. The investigated material is some R260 low alloy steel. The samples were taken from the head of a new rail, and it was some non-textured perlitic steel with some manganese sulfide inclusions elongated along the rail, an intersegmental throw spacing of a few hundreds of nanometers, and a perlite colony size of a few tens of microns. The tensile properties here are relatively modest. And elastoplastic constitutive equations were identified using some torsion and tensile cyclic test. And you can see that there is nearly no isotropic hardening, which will be convenient for computations, since those will converge much faster. Okay, so the testing procedure, we start by pre-cracking the specimen at a constant delta K1. The specimen is then sandblasted in order to get a contrast for digital image correlation, and vacuum annealed in order to remove as far as possible the pre-cracking with residual stresses without changing the microstructure. Then comes the shear-mode testing with a small number of cycles at a constant loading range and a load ratio always equal to -1 until now. And okay, the specimen is then post-cracked using either mode 1 post-cracking or liquid nitrogen-induced fatal impact fracture. And once the specimen is broken, we are able to access the initial and final shear-mode crack front. And by measuring the distance between each of those crack fronts, we are able to access the mean local growth rate. And the aim is then to do the link with the effective stress intensity factors. And here is the difficult part, is to evaluate the effective stress intensity factors, because we have to deal with the friction effects. Because asperities interlocking and friction will reduce the sliding displacement range and the effective stress singularities of the crack front. And this was confirmed by the presence of wear debris on the crack faces after the experiment. And this effect can also be seen on the load displacement loop coming from the testing machine. We have a change in stiffness here at the reversal, which is not meaningful and is only due to the experimental setup. But we also see here some changes in stiffness at the reversal, which are due to the fact that at those reversals, the crack will remain locked at the beginning, thereby increasing the apparent stiffness. And after a while, the crack will unlock, starting from the mouth, thereby reducing progressively the stiffness. And when the crack is fully unlocked and the tip finally sheared, the stiffness goes back to a constant value, which allows us to define an effective cycle and the corresponding fraction of the loading range, which is defined as this effective force over the applied force, and assumed to be equal to the effective delta K over the nominal delta K. But this technique is fast but not reliable due to the gap here near zero load. Another technique is therefore needed. So in order to get a local estimate of the crack face friction effect, we can cast replicas on the sample, since we cannot perform direct observation due to the position of the sample in the testing machine, because it is rotated at this angle alpha. And so those replicas allow us to monitor the crack growth on both sides of the specimen. And the first replica is casted, which is a negative of the surface. And we can then cast a second one, which will be a positive of the surface. And these replicas have to be casted for the maximum and minimum load in order to get the total amplitude of the sliding displacement. but also for zero load, if we want to get the induced opening, indeed, due to the asperities, a sliding of the crack here will lead to an opening, thereby inducing two mode 1 cycle during each reversed shear-mode cycle. So we here have the nominal loading in the K2 K1 space, and the effective loading with the induced K1. And we can get the in-plane opening and sliding displacement using digital image correlation. So this is for mode 1 and mode 2, the in-plane displacement. And since the painted pattern will be incompatible with the replicas, we have to use another technique, which is a sandblasting induced topographic contrast, which will induce a few micrometers wide craters on the surface. And those craters will form a pattern visible on the positive replicas with an atomic force microscope or a digital optical microscope. And once the correlation is done, we use two rows of virtual extensometers 50 microns above and below the crack to get the opening and sliding displacement jumps. So we don't use the full field here because I'm not sure if we know the Williams development for this case, and we are not really in confined plasticity here, so I don't think we can use the full field. And so we can plot the opening displacement in function of the distance logic, and we see that it is often non-symmetric, which is not predicted by usual models with and by plotting this opening displacement as a function of the square root of r, we get the effective delta k1, nothing new. And we will define for the rest of the presentation a delta k shear, which is equal to the square root of the unit times the energy release rate, which will be useful for plots since it combines the effect of both delta k2 and delta k3. And since we are in mixed mode, we need this value. And if we plot the induced K1 over this delta K shear as a function of the delta K shear, we see that there is no clear correlation between those values, and that the asperity in induced K1 lies between 10 to 30% of the delta K shear, which is consistent with models, and that there is more asperity in induced opening for alpha equals 90 degrees, which means predominant mode 3. Okay. Now the out-of-plane sliding displacement, so which corresponds to mode 3. We can use some atomic force microscope measurements on the replicas, which provides a resolution in height of a few nanometers. So the resolution is in fact much better than the resolution of the replicas. But the amplitude is limited to around 10 microns, which is quickly reached since the displacement jump is proportional to delta K3 times the square root of r. So the atomic force microscope is not well suited for measurement of high out-of-plane displacement, but can be used for small out-of-plane displacements. And in the case of high out-of-plane displacement, we use a 3D image reconstruction using the digital optical microscope. So the resolution high is much lower, about 2 microns. And again, we use two rows of virtual extensometer, 50 microns above and below the crack, in order to get the displacement jump. And in order to estimate the crack face friction effect, we have to compare those experimental displacement coming from the replicas with the theoretical one coming from finite element method computation. And if we run elastoplastic frictionless computations, we are neglecting the effect of both crack tip plasticity, which will increase the displacements, and friction on roughness, which will reduce the sliding displacements. And if we do so, we are unable to separate those two effects on the experimental curve, whereas by performing elastoplastic frictionless computation, we can evaluate the effect of friction, which will be the difference between the computed curve here and the experimental curve here. So the extraction of the delta K2 and delta K3 is done by retrieving the sliding displacement measured on side surfaces by those issued from elastoplastic finite element frictionless simulations. So we run elastoplastic computation with various loads until we find the one which fits the experimental curve, and this load will be called the apparent load, and we can define the effective fraction of the loading range as this apparent load over the applied load, which is assumed to be equal to the effective delta k over the nominal delta k's. And for each test, we found that this ratio was the same for mod 2 and mod 3, almost the same, and that it was always almost the same on both sides of the sample. So we use the mean u for each experiment, and we can define the effective stress intensity factors as the mean u times the nominal stress intensity factors. So we can evaluate the effect of friction. And if we plot this mean u as the previously defined delta k shear, we can see that it lies between 0.4 to 0.9, that it seems to increase with the delta k shear. So the bigger the load, the smaller the friction effect. And this u ratio is larger for alpha equals 0, which is consistent with the value of the induced opening from before, because we have more opening for alpha equals 90 than for alpha equals 0 with. And the range of u is consistent with the literature. And now that we have evaluated the friction effect, we can get finally the kinetics and growth rates. So those values are plotted in terms of an equivalent delta k, which is defined as the square root of the effective delta k2 to the power 2 plus beta times delta k3 effective to the power 2. And we have to get the best fit for beta. So the best fit was found to be beta equal 1.3, which is slightly smaller than 1 over 1 minus nu, which is the ratio between K2 and K3 in the energy release rate. So this means that mod 3 is slightly less efficient for track propagation than mod 2. And this beta is consistent with the beta equal 1.2 found by Doke and al for arging steel, and the beta equal 1.1 found by Wojtek, Okuda and al for Armco iron, although the loading range was very different in this case. So the growth rates are between 0.1 micron per cycle up to 10 micron per cycle, so we are in really high growth rates. And if we look at the equivalent delta K, we didn't perform any experiments yet under 0.4 K1C, but for an equivalent delta K between 0.4 and 0.5 K1C, we found no coplanar growth and a direct branching. And for values over 0.5 K1C, we had the coplanar growth, which was then followed by the bifurcation. And the coplanar growth was from a few hundreds of micrometers to more than 1 millimeters in some experiments. But even when we had the coplanar growth, we still found some branching on the crack faces. And those branches can be explained in mod 2 by the existence of a tensile compressive stress along the crack faces. So if we have a branch here, an orthogonal branch, it will be loaded in cyclic mod 1 with r equal -1. And this can be seen on those 3 replicas here, which were casted on the same cycle, but for different load, for maximum load, zero load, and the minimum load. And here we have a branch at 90 degrees, which is open at maximum load and closed for zero load and minimum load. And we can also see a T-shaped branch here at 90 degrees, which then bifurcates at 70 degrees. So the initial King Kong is not 70 degrees as predicted by the models, but 90 degrees in our case. And the effect of such branches has been studied by Khoury and Doke and Frola, and those will have a shielding effect on the main tip. But this is the work of Doke and Frola. And if we consider here a shield disk with a crack and a small branch of length s, we note b, the distance between the branch and the crack tip, we can see that for ratio b over s equal to 1, so the same length here and here, the mod 2 at the main tip will be divided by 2, and we will have some mod 1 on the branch, which will be larger than mod 2, and this effect vanishes as the ratio b over s increases. And such branches also forms in a plane which is normal to the front, while the other one were in a plane parallel to the crack front. So, and they can be seen with tomographic images. So the crack here are this direction. And the nucleation mechanisms can be either shear due to mod 3 or opening due to mod 2. And at the time we don't know which mechanism is responsible for the nucleation. But what we know for sure is that such branches will also probably shield the main crack and lead to its bifurcation. And so, to conclude, mod 2 and mod 3 fatigue rock growth was observed to distance up to 1.5 millimeters in R260 steel for an effective delta K equivalent over 0.5 K1C. The best fit for the equivalent delta K was found to be beta equal 1.3, which is consistent with the literature. And the effective fraction of the shear-mode cycles was between 0.4 to 0.9. So sliding of crack face asperities induces one subcycle within each reversed shear-mode cycle. And the amplitude of mod 1 is between 10 to 30% of the shear modes. And we found that many branch cracks from normal, so shear mode growth plane, and will shield the main tip, thus promoting bifurcations at 90 degrees, but this deserves further analysis. And a new marking technique, which is sandblasting, has been developed for digital image correlation with replicas. And additional tests will be run at different error ratios and for smaller delta Ks in order to see if limited coplanar growth is found, as witnessed by Okuda and Gosteig and Heli and Al. And I thank you for your attention.